In this first collab, we're gonna do a simple linear regression. You're not gonna just call a function that will do the regression for you. We're gonna do the regression, the fitting, model fitting by hand. So you have a better understanding of the steps that are executed for optimizing and building a model. And that will give you a better idea of how the neurons implement those linear models within their structure. I have presented before this simple linear equation from linear algebra. The linear equation of a linear model basically consists of your y value, which is the ground truth data that we want to predict, that is equal to m, that is a slope or the model weight in the linear curve, that is multiplied by x, or a set of x, your set of inputs that should be related to y. So you are basically here using x to predict y. And then that multiplication is summed by a bias value, or the intercept, which is the proportion of y that cannot be explained by x. So we have this linear equation, but let's get started. Let's start our implementation. Let's see how that linear equation is implemented in Python. But before that, we need some data to train. And I mentioned before, we're gonna provide all the data that you're gonna use for fitting your models here in this course. And the way that we generate our data, as I mentioned, is by simulating some linear data. And the formula for simulating the data is basically the same linear equation that we saw before, but we add a little bit of error. We add a little bit of random noise. If we did not add this random noise, we would have a perfect x and y matching. So there would be no fluctuations, no difference between x and y. And then we would not need a model to fit. We would not have to fit a model because it would be just x equal y. There is no puzzle to solve. So we have to add some noise for simulating our data, and our noise is random sampling extracted from a normal distribution with a mean of 0 and a standard deviation that we can customize. As bigger is the standard deviation, more fluctuations, more noise we may see in our data. So we're gonna start by importing the package that will have all the functions that we need for simulating the data, which is the scikit-learn, or sklearn for short. If it's the first time that you are running this, it's gonna ask you if you wanna trust this notebook because it was not developed by Google. We can just run anyway. And then you're gonna see that the server will connect, and we should be able to see a little check here. All right. And then after that, we can just do some debugging, just a sanity check to make sure that we imported our package. We see the package version here. If the import did not work, we would get an error because this variable would not exist. So we also need a submodule inside sklearn. This submodule here is the submodule that has all the data simulation functions that we're gonna be using. So that's why we're gonna import this little submodule just to make things easier. And inside this submodule that belongs to sklearn, we have a function called make regression. That's the function that creates this synthetic simulated data set. There are a few input arguments or input options in this function. One of them is the sample size. As bigger is the sample size, we're gonna take longer to train and converge our model. So we're gonna start with a small sample size just for this demonstration. Number of features as well. We can set with the number of features how many predictors we want to have in our model. So how many x dimensions? In our case, we're just gonna have one x for predicting the y values. So it's just one feature. And then we have the bias, that is the intercept that I mentioned before, and the amount of noise, which is that error from the linear equation with the added random sampling from the normal distribution. And we have a random state, which is the random seed. This algorithm, if you run it multiple times without the random seed, you're gonna get a different set of values every time that you run it. So we can fix the random state, the random seed, so that we run multiple times and we still get the same result. So you can run that. It's pretty quick, already finished. And if we print our x and y values, you're gonna see a 2 vector with 2 groups of values. It's a little messy here. So I recommend that you print your y separated from your x, so you can understand which one is really X and which one is really Y. So it's just a set of random values that we generated. I see a question here in the chat. Is that dimension the tensor? Here, we are not working with tensors yet. So this is just a list. It's just a vector. So we are not talking in terms of tensor ranks or tensor dimensions yet. But in the next example, then we're going to start to convert our data into tensors. All right, let's continue here. So we have our X and our Y. We can tweak some parameters. For example, if you want to create more features, just to show an example here, then you're gonna see that now instead of being just rank 1 vector or X, now has 2 groups of values. So it became like a rank 2 vector with 2 sets, 2 groups of values. So we can use this simulation function here, this make regression function, to simulate as many predictors as we want to make a model that is as complex as we want. And as we add more X's, so we had our X1 that we simulated before, this X, the new X2 that we have here, we have to also add more slopes or more weights. So weights that we're going to have a weight that will be multiplied by the first X and another weight that will be multiplied by the second X. So then we can fit both of these X values to Y. Since they are different, they will have different slopes. So let's just keep going here. Let's get back to our simple X. We don't need to work with multiple X's to go through this exercise. The real goal here is to just get a simple X and Y and then fit the data. So let's stick to that. And for plotting our data, we're gonna use the PyPlot submodule from the matplotlib, which is a data plotting library from a data plotting package from Python. And in Python, we can rename those submodules. If we have like a big name like this, we can just use the as and then choose a name, a new name for the package. So it's a good practice. If you have a package that has a very extensive name, you just shorten it a little bit. And that's what we're doing here. So instead of writing down all that name, we can just shorten it and type PLT instead of typing matplotlib pyplot. So after we import our package, we can use the scatter function inside the PLT submodule to plot the data. So we have here a very simple X and Y. It's still very linear. So we set a very small noise before. Maybe we have to increase the bias or the noise and see, let's see what happens if we increase the bias first. It didn't change the noise, it just changed the range of the plot, as you can see. So it's just the intercept that is changing when we increase the bias. Now let's do the opposite. Let's return to the bias that we had before, but let's increase the noise a lot. Now we have more fluctuations. We preserve the same intercept, but now our slope has much more noise than we had before. Before we had with a small noise like this, we had almost a perfect fit, but now we have a simulated data that has a bit more noise that we can start working with. So here we have a positive slope. If you want to invert that slope to make a negative slope, you can just multiply your Y by a negative number. So if you want to flip the data, you can do that. Those are just additional things that you can do for simulating data. I'm just showing you that. So when you start to draft your AI model and you don't want to waste time dealing with importing your data and pre-processing your data, you can try to simulate a data set first, just to do the exercises, just to learn how to implement your AI model. And then when you feel safe enough, or you feel that you learn enough with the simulated data, then you can take that model, use your data to train the model, and then start to adapt and tweak your model to fit to your data instead of using the simulated data. So it's pretty useful to know how to make some simulated data sets to start doing your exercises implementing the neural networks. So this is just another example where we have a high amount of noise and we flip our slope to be negative, and we add a little bit more samples. So instead of 10, we have now 50. So we have a little bit more data points to play with, but still a small data set. And we are still fixing the random seed. Now let's jump into the model itself. So how we create our linear model from scratch. So in Python, there are functions. Functions is basically a chunk of code that you define a task that it does, and it is callable. You can define this chunk of code, you can define this task, this function, and then call it later whenever you need to do that task. So usually when you have a task that you have to rerun several times, it's a good practice to create a function so that you don't have to keep copying and pasting the same code over and over. You just you define the task, and then you run the task again, referencing to this definition here. So to define a function in Python, you use the def instruction here and then space, and you can choose any name that you want for your function. In my case here, I'm choosing a linear model because we want to create our linear model here. So we try to keep informative names, and we can choose any set of input arguments or options for our function. In our case, sometimes we have input arguments that don't have any default values, and then we can have also options that have default values. That's why you see the equal sign here and a default value. Those values can change when we call that function later, so we can adjust those options as we want, and we can provide new x values as we want as well. But in this case, the x doesn't have a default. After we define the function and what arguments it takes as input, we can define also inside this function what it returns. So you see an indentation spaces here. So those indentation spaces are telling that when we advance an indentation, that this code belongs to this function. So that's why we have to add an indentation. If we didn't add this indentation, then we would say this code doesn't belong to this function. So in Python, unfortunately, those indentations are picky, and you have to pay attention to that. It's not like in R that you can just open parentheses or close parentheses to tell that a chunk of code is part of that loop or that function. And here, what we're going to return from our function, the value that is going to return is the result of the multiplication of our slope or model weights by our axis. So this is basically the first part of the model. And then after we have this multiplication done, we sum the bias or the intercept. So this is basically the linear equation. So very simple model. This is basically the task that a linear typical neuron would do if you were just creating a linear regression model. We have defined our model. Let's run here. Okay, so we have executed this. We have defined our model. Nothing happens because we are just defining it. We are not running it yet. We're gonna run it later here. So for example, I can call that function that I defined before by specifying its name and providing an x value. So the x value can be one scalar value or a vector of values as well. And since there are default values for M and B for the weights and bias, I don't need to provide them just for testing. I can customize them later, but just for testing, let's just do this. And I'm setting a new Y value here just to store that result and then print it later. So let's do that. So we have basically a bias of 0 and a weight of 1. So we are multiplying our x by 1 and summing to 0. So what we expect to see is exactly the same y equal x. So that's the simplest type of test that we can do just for debugging that the function is working. We're just returning an x equal y. We're not fitting anything yet. We're just calculating this formula here. So the linear model is working. It's doing the simple calculations correctly. Now let's play with some additional parameters. With the default M and B, we just have an x equal y. Let's see if it's able to modify the x to return the y value. So yeah, so it provided an input of 10.2. We flipped the slope and we add a little bit of intercept. So yeah, it switched the sign from positive to negative, and it slightly changed the value. So our linear model is working. This practice of doing very simple and dumb examples, just doing those sanity checks, are a very good practice when you are implementing your models or any sort of function. You know that the function should be doing what it's supposed to do, but it's better to manually go and check if it's really doing what it's supposed to do. Sometimes you think that your calculations are correct, but sometimes any typo or mistake may happen, and then your linear model or your function will not be doing what is expected to do. And then later you find a problem downstream in your code, and you have no idea why that problem is happening. And then you would have to go all the way back and start debugging from scratch. So if you have those checkpoints where you do debugging and you just do those sanity checks with very simple, silly inputs, it's better that you do that in advance instead of waiting until you find an error or a bug in your code and you don't know where to start searching for the solution. Let's go ahead now after our tests and let's apply this to a real x. So far, we just tested on a simple scalar value. Let's see if our linear model can be applied to a whole set of 10 samples of x, right? If it would have any problems, it would return an error, but it returned a vector of predicted y's resulting from calling that function that we created by transforming the x and just using the default parameters. So the default parameters are m equal 1 and b equals 0. So the x should be equal a y here. And the only difference here is that we inverted the slope just to add a bit of variation to our data. So we have simulated our data, and now we can basically create another function just to plot this data that we simulated and that we predicted with our linear model, just to make things easier, because we're going to have to plot many times. So again, when you have a chunk of code that you have to run many times, it's always a good practice to create a little function that will do the job for you, so you don't have to keep copy and paste code. You just call that function by name and you don't have to repeat those contents. So we can define our function and plot the x, the y, and the result from our linear model to see how it looks like. So we have our simulated data, which is the x and y, and we have our predicted linear model using the default parameters, the default m of 1 and b of 0. So that's why you see that it's crossing the 0 here in the intercept of 0. And then you see that it's equal, it's multiplying x by 1. So it's basically equal to x in every horizontal axis here, every data point. So we just made a linear model that returns bias intercept of 0 and an x equal to our predicted value, multiply the x by 1. So we are just returning x with an intercept of 0. So that's our default parameters. Now we see that our model is doing just a bad prediction. Of course, we have not fit our model yet. If we're using the default weights and biases, it's just a model that doesn't do a great job. It's not trying to the data. It's not adjusting the weights and the bias so that we get close to the real data as possible, to our observed y's as possible. So now we can say by looking at this that our predicted y's, the y hat, they are not fit. They have not been fit to the data. They don't look like the data that we have observed. So the next task is to try to adjust your m and your b, your model weights and the biases or slope and intercept, so we get as close as possible to our training data, to the observed data. So we start with an m of 1 and the beta of 0. You can, if you want to follow along and and do this exercise, you can play around and change those values. So let's start trying to adjust. Let's see, let's try to increase the weights. So we have a positive value, so it's actually having a positive slope. If we want to have a negative slope like that, we probably have to flip the value. Okay, we're getting closer. So let's try to increase this. So this is just a kind of feeling. You are instinctively adjusting the values to see how close you can get to your training data, how fit you can get to your training data. And this process of trying to adjust things is basically what the optimizer does in the neural network, for example, when it's applying that gradient descent algorithm. When I was explaining about that, we have like a valley of possible weights and possible loss values or model error values. And we drop our model in this valley and we ask the model to go downhill to minimize the amount of error. It's basically what we are doing now. We are trying to minimize the amount of error. As closer we get to the training data, as more fit we get to the training data, we're minimizing the amount of error of our model. So we are basically doing an optimization, a training algorithm by hand right now. So I hope this experience can help you to understand what is the algorithm of model fitting, what it means to train your model. So you're basically training your model by trying to get closer and closer to the to the training data. So we're getting a bit closer. I could do better than that. You'll probably be able to do better than that. I'll stop right here. The way we quantify the model error, but we usually call the function that we use to calculate the amount of error of a model as a loss function. So you're gonna hear the term loss many times. That basically means that the loss function is a function that we use to tell how bad or how well our model is doing. Usually we calculate the amount of error. So we are telling how bad or how poorly our model fits are doing, or how bad it fits to the training data. So the most simple of all loss functions is the mean squared error. You subtract your ground truth, your observed y values, your response variable from your predicted data, your y hat, and you square that, and then you sum all those square of differences. And then you divide that by the sample size, which is n here, to calculate the mean value. So it's a very simple equation, and it's going to tell us on average how bad our model is, how different our predictions are from the reality, from what we observed in the training data. And let's go ahead and implement that function. So actually, it's very simple to implement it. We don't have create custom function to do that because the submodule metrics from scikit-learn already has that function pre-implemented for us. So that helps a lot. So we don't have to make function from scratch by hand using the definition, the def chunk of code that we were using before for the linear model. We just call the mean squared error function from inside the metrics submodule. And that mean square error function here from scikit-learn metrics, we will apply exactly that equation that we are talking about. Let's see how bad our linear model does with the default parameters, right? Those are the default. Remember that flat line that just multiply the x by 1 and sum to 0. So it had really no slope at all, and it did not fit well to the data. Let's see how that bad model did. So we are defining our predicted y or y hat here, and we are comparing that to our observed or ground truth y, our response variable from the training data, and we are storing that into an error variable, and we're gonna print that result. All right, so you see the amount of error is really, really big. Let's go back now and see what were the best fitting parameters that we had. We have minus 50 and 30. So let's try that and see if the error changes. Minus 50 and 30. It's much smaller now. I think we could do better, but I'll let you play with those numbers and yeah, just play around around and see if you can decrease the amount of error until you get, oh, we got much better. Let's see how it looks like. Yeah, very close. Some of the points here are kind of perfect. Yeah. So you can play with that, and you basically see if it's colder or warmer, and then you try to adjust based on the error. That's exactly what the training process does. That's what we do when we say that we optimize our models. So we add an optimizer to our TensorFlow model, to our neural network, and we tell that we want to fit our model to the training data. We are basically doing this whole process that I showed you. We start with default weights and biases, or random. Usually, typically, we start random, and then we keep tweaking it, changing, doing slight changes, and calculating what is the direction that we should go. In our case, we are just doing by feeling what is the direction and trying to adjust it. In the case of training artificial neural networks, and linear regression models, as we are doing here, we usually use an optimizer algorithm that will do the training for us.